So far we've looked at supervised learning in a way where we try to find a function that maps some features to a class. What we're going to do now is going to do something more case-based, the idea being that you're going to try to relate the thing that you see right now to a particular thing that you might have seen in the past, and then maybe you could see what the label was of that thing in the past and then just transfer that label over. That's the key idea of what we're going to look at. So why would you want this? Well, if you have inseparable data, if you don't know exactly what, maybe you can design interesting features that will make this separable by, having an additional third feature that brings it into 3D, and somehow now it's linearly separable. And if you have good knowledge of the domain, you might be able to do this. There's just something else that doesn't require you to do that we're going to look at now. So the canonical thing to do is something called, or kind of canonical starting point is something called one nearest neighbor. And what that means is you look at all training data you have seen, your test data point comes in, you compute the features for your test data point, you look at your f of x, compare it to the f of x of all your training data, check which one is the nearest by just taking the difference between f of x of the test data and each of the training data. Whichever one is nearest, you look at the label, you say, okay, that's what I'm going to predict for this test data point. You can do something that's a little more robust to noise. Let's say some of your labels are wrong. You could say, I'm not just going to take the nearest one because maybe that happens to be one that was labeled wrong. And let's assume most of them are labeled right. Then you could say, I'm going to look at the k nearest ones, maybe 10 or maybe 11. And then you're going to just take a majority vote of these 11 that are nearest, which class were they assigned to originally in the train data, and you just take the majority vote. Maybe you could weight that vote by the distance to these points. So a point that's closer to your new test data point will contribute more to the vote than one that's a little further away. Now the key challenge then, of course, is what does it mean to measure distance, right? Because how you measure distance is now going to define what is most similar and what is less similar. If you rescale a coordinate and you multiply it by 1,000, then now everything on that coordinate axis will look very far apart, right? And you're really emphasizing that coordinate axis then, because distance will be mostly determined by this one coordinate axis where everything is really, really large. So you need to be a little careful about how you measure distance. Let's take a look at kind of the bigger context before we dive into exactly how we're going to measure distance. What we're looking at here is for the first time something called a non-parametric model. In contrast to what we've seen so far are parametric models. In parametric models, you have a set of parameters, and you somehow set them based on the training data. And the more data you get, the more accurately you'll be able to set those parameters. But by fixing the set of parameters that you're willing to learn, you're also fixing the class of decision boundaries that you could possibly come up with. If you say linear classifier with these three features, that fixes what you can find. No matter how much data comes in, it will always be a linear classifier with just these three features. So it doesn't allow you to naturally get a more complex decision boundary, which you might imagine you want when you have more data. You can imagine the more data comes in, the more complex you're willing to make your decision boundary because you have more evidence to support that complexity. In non-parametric models, that comes for free for you. The more data you have, the more complex your decision boundary becomes. So let's take a look here at k nearest neighbors, which is a non-parametric model. We have two examples. There is a negative example here, a positive example here. And if we compute for each point in this 2D space, the nearest neighbor, and color it green if the positive one is nearest, and color it white, or leave it white if the negative one is nearest, then you get a picture that looks like this. So you actually get a linear decision boundary if you learn from just two examples. Now, let's say we collected more training data for this particular supervised learning problem. 10 examples, then it looks like this. This is pretty complex. Is this what you want? That's hard to say. This might not be what you want. You might say, that's pretty complex. Learning something this complex from 10 examples, I might be overfitting my training data. That's possible. 100 examples starts looking like this. And then 1,000 examples, we get this decision boundaries over here. So how did we generate this data, or how did the web demo that gave us these plots generate the data? It started from a decision boundary that the programmer put into the system, and then randomly sampled points, and wherever they fell in the positive or the negative class, that would be the label, and then you just feed in training data that way until you reach here 10,000 examples. That original decision boundary, the ground truth from which the data was generated, but in a practical problem you'd never know what the ground truth is, looks like this. Now, of course, if you knew that the ground truth is this thing that has a pretty clean structure to it, you might want to design features that better capture that structure than just do nearest neighbors. You can see it can take, a little while to really figure out what that structure is. Even after 100 examples, you don't really have it fully recovered. In fact, you still would make a lot of mistakes, even though this is not the most complicated decision boundary. But in practice, you often don't know exactly what the decision boundary should look like, what types of decision boundaries you're willing to consider, and so this is very flexible. In the limit of infinite amount of data, you'll get it right, assuming your data is not too noisy. All right, it's also a very simple algorithm, very easy to implement, right? Just find the nearest one or k nearest ones and do a vote. Here is an example for digit classification. You look at digits, maybe these were your training examples. A new one comes in, and now you just need to compute which of these training examples was the closest image to this new one that came in. Well, there's many ways to compute the closest. You could encode this as a vector of intensities. Then you could say, this one is that vector, and all of these have their own vectors of intensities. You could say, which is the most similar one? Say, well, what's the reasonable similarity function between vectors? One way to measure similarity between vectors is to actually take the inner product between the vectors. Because if they're pointing in the same direction, then inner product will be really high. If they're pointing in opposite direction, they'll be really low. So that's one way to measure similarity. You take the dot product, in this case the original pixel values, and this is what you get as your measure. And then you can, in this case, you're not measuring distance, you're measuring similarity, so you would find the example in your training data that has the highest similarity to this new test example. All right. In practice, often you'll normalize your representation, so you wouldn't have arbitrarily scaled things to deal with. Assuming you keep things between 0 and 1, then everything would be positive. So 0 would be the lowest score you can get, and 1 would be the highest score if everything were normalized. That would give you perfect alignment. So this is one example of how you can measure similarity. You might wonder, why are we measuring similarity now rather than distance? The reason is that later this lecture we'll be able to relate nearest neighbors based on similarity back to the perceptron algorithm. But we need to do nearest neighbors based on similarity to be able to make that relationship more precise than we could based on distance. All right. So then now our question becomes, how do you design similarity functions? All right. This thing here might not have been the best thing. You can imagine that just making a vector of intensities, if that digit had been shifted over just a couple pixels, almost nothing would have been the same, and it would not have found that as a similar thing. If you have enough data, not a problem, you'll have all versions, all shifted versions. But if not all that much data, you want your similarity measure to be more reflective of what is really similar in terms of what the label is going to be than just doing an inner product between the original pixel values. So what you would do is, just like we did for Perceptron and for naive Bayes, you would put things in a feature space. So you compute features, and then you would take the inner product between the feature vectors. In this case, similarity between incoming x and x prime, you'd compute the feature vector for both of them, and then take the inner product between them. That's one way to do it. And another way to do it is to potentially say, use what we had before here. But one thing to keep in mind is that they don't have to all be of this form. And in principle, you don't have to work in feature space. A nice property of working with these similarities is that you could define any function, sim x prime, so a similarity function that takes in 2 data points and outputs a number that reflects how similar they are. So you don't have to go through feature space if you don't want to. You don't have to think about what the features might be. right? You could have something where you say, oh, what is the minimal deformation I can do to this new image that comes in so that it maps onto a training example, and measure in some sense how much you're deforming, shifting pixels around to get it to match. And then that could be your similarity measure. The less you have to deform, the higher the similarity. Really anything that you can come up with that, according to your knowledge about the domain, would measure similarity, you could use that directly in these nearest neighbor searches. Now in practice, it turns out that a lot of the really good similarity metrics that you'll be able to come up with actually correspond to some feature space. You might not know what the feature space is. In some cases, the feature space could be really, really large, and it would be very expensive to first go to the feature space and then compute the inner product, and it'd be more efficient to directly compute your similarity. But it turns out that for many things that people use, this feature space does exist. So often it's good to think of it as two alternative ways of doing the same thing. You could go to feature space, compute an inner product, or in many cases of similarity functions, you could equivalently use the similarity function directly and work with that. And it just depends on what's fastest to compute for you, what you want to do. Similarity function versus feature space. When you do math, whenever there's an equivalence there, you can decide whatever is easiest for you to work with. You say, oh, to do this math, I'm going to work in feature space, and then maybe derive some properties of this particular algorithm. And doing this other part of the math, I'm going to work directly in similarity function space because it's easier to work with that for this part of the math. So at this point, we've seen two very different types of approaches in that nearest neighbor, non-parametric, similarity function. You're really going through your training data and checking what the most similar thing is. You have two ways of doing that, through feature space or directly through a similarity function. Perceptron-like algorithms, what you do is you actually have something going on. When you get your data, you don't just say, oh, in the future I'll look up in the data what's nearest. No, you actually have a training phase. You use your training data to find some parameters, and then that gives you a decision boundary that you're then going to use in the future. Let's see if we can get the same kind of non-parametric representations into our perceptron algorithm, such that we can in some sense get the best of both worlds. We can get this kind of non-parametric representation from the nearest neighbors, but at the same time we're using it in a way where when we look at all the training data, we use that to learn a decision boundary that is inspired by all the training data. The thing here, or the kind of buzzword or keyword, is kernelization. We're going to kernelize the perceptron algorithm, and that will make it very similar to a nearest neighbor algorithm if you choose the right kernel. For kernel, you can really think of as the same thing as a similarity function, but for kernel, people tend to assume some mathematical properties are true, so not just any similarity function would work, but most of them will actually be kernels if you pick them reasonably. Okay, so let's go back to perceptron. Let's say you run your perceptron algorithm, and you find the weight vector wy for some class label y. Can it be any real vector? Let's say you work in a two-dimensional feature space. Can it be any point in that two-dimensional feature space? Could that be your wy? Maybe not the zero weight vector, because that might not get your training data correct, right? It'd be kind of a weird weight vector. Let's think a little more about, in terms of what it could be as a function of the training data you get. For a specific set of training data, what could it be? Well, let's take a look at the updates. So the update equations look like this, in some sense. So whenever there's an update, either you add a feature vector or you subtract a feature vector, which means that the only weight vectors you could ever find are weight vectors that are a sum, addition and subtraction of feature vectors in your training data. So not everything is possible. This is a special structure that you get in your weight vectors. We're going to write this as follows. the weight vectors that we find are always going to be of this format. And really what we're doing when we're training a perceptron is we're finding these coefficients alpha I, y. These coefficients tell you how often a particular training data point xi was added into the weight vector wy. Right? So I indexes into your training data, y indexes into your different class labels. All right. So now we're going to see what we can do if we work with this dual representation. We're going to consider the perceptron algorithm, and instead of learning a weight vector directly, we're going to learn the entries in these alpha vectors. We know that that will be equivalent, but we're going to look at what happens if we do that and if we can get any benefit from doing it that way. All right. So one thing we do when we run the perceptron algorithm is to check the score when a new example comes in, wy times f of x, which is an inner product, right? Okay, well, that's now going to be the sum over alpha I, y, f, xi, where this is your current, from your current alpha set of alpha I, y's, right? So instead of having a current weight vector, you have a current set of alpha entries. Based on those alpha entries, you can compute the weight vector, and then you can compute this thing. We can expand this by bringing the alphas out. And what we see now is that computing the decision for a perceptron comes down to inner producting every training example, fxi, that you have seen so far with a incoming feature vector f of x. So we see that effectively the perceptron is actually computing similarities. And unlike the nearest neighbor, nearest neighbor would compute all those similarities and then say, oh, let's pick the one that has the highest similarity. That's my prediction. What you see here that perceptron is doing is computing all those similarities, but then for each class, there is a coefficient that is saying how much that particular training example contributes to that class. And you can contribute in positive or negative way, right? Because these coefficients alpha I, they're composed of pluses and minus, +1, -1. And so whenever you have a term here, it could either be something that was indeed labeled with the label y, and you got a plus f of xi because you got it wrong in the past, or it could be something that was labeled with something else, not y, and by mistake you had predicted it as y, and then you subtracted. You had a minus f of xi contribution to the weight. And then you'd have a negative entry in the alpha. Now we can rewrite this, and we can call this quantity over here kxix. This here, in our previous slides, we would have called simxix. We call it k here because we're not just having an arbitrary similarity function. We're using a similarity function here that we know, just because we wrote it that way, is an inner product between some feature vectors in a feature space. Okay, so what we see here is that if we evaluate something for a perceptron, to do the classification, we could do that in the same way we thought about nearest neighbors. It's now a weighted sum of similarities that we use to make a decision. Each class has its own set of weights. You compute all the similarities with the training data, then do a weighted sum for each class, and you see which class comes out on top. That's your prediction. So this is a very strong similarity. What's different between this and nearest neighbors? Nearest neighbors, the alpha I, y entries would be all 0, except for the one entry that's closest to the test example x. All right, so what if we run training? We know how to classify an example, so we can do this now with this equation over here. We keep track of the alphas. A new example comes in. We try to classify it. If correct, no change. Alpha entries stay the same. If it's wrong, we have this set of updates over here, which is translated in this set of updates on the left now. What is that saying? This should be xn here. This is xn, xn. So it's saying that I would have updated wy by subtracting f of xn. Well, how often f of xn is added or subtracted is kept track of in alpha yn. So alpha yn has to lose an amount of 1 here. Same for y star. We would have added f of xn to wy star. Since wy star is a weighted sum of feature vectors and the contribution of f of xn is stored in alpha y star n, we add 1 to alpha y star n. Yes? Okay, so what is the difference between what we're doing before and now? We are looking in the dual space, as it's called. We're doing the same thing, but we're looking at it from a different perspective. So instead of directly working with the weight vectors, this is here just for analogy, but this would actually not exist when you run your algorithm in the dual space. If you run your algorithm in the dual space, you would just be updating the alpha entries. So your weight vector would never exist. Aside from that, you're doing the same thing. It's just a transformation of variables is one way to think of it. And we work with this new set of variables that are equivalent to the old set of variables. But the beauty of this transformation is that if you work with the alpha variables, you can use these similarity functions inside your perceptron. Whereas if you worked with the original variables, the weight vectors, you had to work directly in feature space. And so whenever you have a similarity function for which you maybe don't know what the feature space is, or the feature space would be, some cases the feature space can be infinite dimensional, even though your similarity function is very quick to compute, then you're much better off working in the dual space, because now you can just compute that similarity rather than computing an infinitely long feature vector, then inner producting two infinitely long feature vectors and do all that work, which will take forever. Any other questions about this? Yes? Can you say that again?
Wasn't that my choice what the feature vector is?
Yes. The feature vector is your choice, and by going into the dual space, you have now expanded your set of choices to not just choosing potentially a feature space, but you can instead now choose a kernel, which computes similarity. So you've expanded your set of choices. All right, so that's the kernelized perceptron that we just covered. You work in a dual space, and you work with similarity functions rather than with feature vectors. At this point, it's a lot like nearest neighbors, right? The result here, if you score a class after you've done the learning, you do something like this. One way to think of this is that it is like a nearest neighbor classification method, but the way you're voting here, right, these weights alphas are votes in some sense, right? How much does this training example contribute to the decision that we're going to make? And so the alpha entries allow you to weight certain training examples more than others, potentially weight some negatively if you want to do so. And that gives you a little more flexibility to learn these alphas directly from training data, whereas if you did nearest neighbors straight up, you would just have some kind of weighting scheme that you fix, maybe equally weighted for your nearest neighbors, and that would be it. So you would, standard nearest neighbors, you have no direct way to adapt to your training data. This kernelized perceptron does adapt to your training data and can learn a decision boundary that is inspired by your training data, which the nearest neighbors wouldn't do. What's the downside of this dual space? The big downside is that, well, if you have a lot of training examples with a non-zero alpha, then those are all the ones you have to consider, right? In this summation here, whenever alpha I, y is non-zero, you have to compute a similarity, and that contributes to your computation. So that's the downside compared to the primal perceptron. For the primal perceptron, to make a decision, you just have a weight vector, you compute a feature vector, bring them together, and there's your decision. Here you'd have to compute, you have to store your data, keep track of your data, because you'll still need it. All the data has a non-zero alpha I entry. You'll have to keep around to make decisions later. All right, so why do you care about these kernels, aside from maybe you could work now with similarities rather than with features? Well, it can look strange, but this kernel trick idea is that you can substitute any similarity function in place of the dot product. Not any. They have to satisfy some mathematical properties, otherwise some proofs will break. But most things that you'll come up with will satisfy those mathematical properties, and so allow you to directly work in that similarity space. Now, you can learn new kinds of hypotheses that you couldn't learn before, or would have been much harder to learn, such as nonlinear hypotheses, as shown here. An example of a kernel that is, for example, very popular would be something like e to the minus 1/2 norm x minus xi. Let that be the 2 norm squared, and then this would be divided by some sigma squared. What you have there is essentially a Gaussian kernel. This is measuring the distance between xi and x over here. That's the distance measure. And it's saying, well, of course, we want to measure similarity. So with this Gaussian blob, the closer you are, if that distance is 0, you have the highest possible score, and it decays from there. What you get with that is something a lot like nearest neighbors. You get something where things that are close by have a very high similarity, things that are further away have very low similarity, and that similarity exponentially decays. So essentially you will end up voting based on the nearest neighbors, but in a way that's tuned a little more than just looking at the nearest neighbors. Yes?
Could you give an intuition why it's called Perceptron?
It's called kernel because it represents to an inner product. That's like your spirit. So, I mean, if you want to look up more keywords, more mathematical formalism, the thing to look for would be the term called reproducing kernel Hilbert spaces. And that's where you'll find what exactly is going on here, when it's a RHKS kernel or not, and then that means that you're working with a correct kernel. All right, so using these kernels, we can now learn nonlinear decision boundaries with the perceptron. All we have to do is pick a decision kernel or potentially alternatively nonlinear features that correspond to that kernel to get a nonlinear decision boundary. So let's take a quick look at these additional features that you might be picking. In fact, some of you already picked them if they completed their homework 9. Here's the first data set. Linearly separable, no problem. How about this data set here? Not linearly separable. So we need if we think that these labels are the right labels, as opposed to noisy labels, right? Then we wouldn't want to learn a linear decision boundary, because then we'd just be able to make a cutoff, and on the left is positive, the right is negative, or the other way around. We want something more complicated here. So you could say, well, let's lift it into an additional dimension, and now we can actually draw a linear decision boundary right here. It's a very general trick that you just kind of throw in extra features, ideally inspired by some understanding of what the data is like, and then you might be able to come up with a linear decision boundary in a higher dimensional space. Now, the thing to keep in mind here is that what we're really doing here is we're saying, look, we have these great algorithms to find linear decision boundaries, such as Perceptron. We don't have as great algorithms to find nonlinear decision boundaries, but we know some data need nonlinear decision boundaries. And here we're playing a trick to make our data higher dimensional. And a linear decision boundary in the higher dimensional space is actually a nonlinear decision boundary in the original space. Because this thing over here, if you map this back to the original space, it would put the decision boundary here and here for these data points, right? You would classify the things in the middle differently from the things on the side. So somehow you've found something nonlinear in the original space thanks to mapping it to the higher dimensional space. You might want to do this in more dimensions. This you might have already done. So you have this thing here. Inside the circle, red class. Outside of the circle, the blue class. That means the further away from the origin, the more likely it's blue. So you're going to maybe introduce an additional feature that says distance from the origin is the additional feature, and now you can more easily separate the blue and red class. Yes? These are the previous features, so this would be x1, x2, or it could be f1 of x and f2 of x, depending on what you are working with. Absolutely. Okay, so why kernels? Why these additional features? It really depends on your particular problem setting. Right? If you can come up with features that are very well inspired by your problem setting, and maybe throw in a couple of additional things like the product of all features and the maybe squared value of all features, then maybe that's enough and you can find a linear decision boundary, and there you go, your perceptron can classify your training data, hopefully your test data. Often it's the case, though, that to come up with interesting features, that feature vector will end up being pretty long. It could take a lot of computation. So there are a lot of examples of, let's say you have the thing where you say, oh, I'm going to work with a feature vector that has all products of original features in it. Then it turns out that there is a kernel that is much faster to compute, that computes the same thing as you could compute in your feature space. And so a lot of the tricks people played back when this became popular in the late 90s, a lot of the research papers would be about, hey, look, this really complicated feature space, which is really interesting, can be captured by this similarity function that's much faster to compute than yours going to that feature space. Doesn't have to be the case. One of the nice things, or one of the kernels that's used the most, is the Gaussian kernel, the one that I put on the slide earlier. That one's very generic. It's essentially making your parametric perceptron algorithm into a non-parametric algorithm, because this Gaussian kernel is just going to look nearby the point you had. And so you get the benefits of a supervised learning algorithm that tunes weights and so forth, in this case in alpha space, while using a non-parametric representation by using these Gaussian kernels. Okay, any questions about kernels and going to higher dimensional feature spaces? Yes? Okay, so why would you add the extra dimension here? This is just a kind of a picture to illustrate the point that by adding an extra dimension, you could get the benefit. In practice, probably it would look more something like this. You'd have a feature vector. F1 of x is the first entry, F2 of x, F3 of x, F4 of x, and you keep going till maybe F100 of x or 1000 of x. So you wouldn't have an easy time plotting this and analyzing where your decision boundaries should be. You have to work in some representation that you can't really visualize, because this is 1,000 dimensions. And so you might run your perceptron, look at your training data, accuracy of your training data, and you say like, wow, I have 1,000 features, so I should be able to, let's put it the other way. I have 1 million training data points, which means, rule of thumb, I can work with 1 million over 5 features, which is 200,000 features. But I only have 1,000, so let's generate more features, because I know that I have enough training data to deal with more features, right? And maybe I'll do better with more features because I have more freedom in terms of finding something. And so you'd say, well, how am I going to generate more features? I can't visualize this. I don't know what it is really that matters. So you could say, oh, well, I'm going to have a feature vector, new feature space where we have f1 squared of x, f1 of x times f2 of x, f1 of x times f3 of x, and so forth till f1 of x times f1000 of x. Then I'd move on, f2 of x times f1 of x. It's a little redundant, but that's fine. f2 of x squared, and so forth. And so you'd kind of arbitrarily try some things out, maybe not completely arbitrarily, but you just try some things. This would be all products of features, right? All pairwise products. You could imagine doing all triple-wise products. You'd use a Gaussian kernel maybe with different widths. And in practice what you do, you'd run your perceptron with all these different choices of kernels. You'd look at your holdout data, which one of these kernels or feature spaces did the best. And you'd say, oh, that's an indication that most likely on the training data, I'll do best with this particular set of features that I picked here that did best on the holdout data, and that's then what you retain and work with. So it's really giving you just lots of options is the idea here. Yes?
So the last slide before this saying that you add some more features that you might be able to solve it linearly in the high-dimensional space?
Yes. If you had enough features, you'll be able, in fact, if you have enough features and they're generic enough so your points are not chosen in particularly weird ways, you can prove bounds. So if you start thinking about learning theory, which we're not going to cover in this class, but learning theory is the idea of, if, let's say, I'm willing to consider only linear decision boundaries in a, let's say, k-dimensional space, how many training examples do I need to be able to learn, right? And often the way that learning theory works, so some of the ideas in that learning theory is something called VC dimension. And VC dimension says the following. It says that if I had k data points, not k, if I had a k-dimensional space and I'm willing to go with linear classifiers, how many points can I put in that space such that no matter which way I label those points, I can always find the decision boundary? If that's true, if you have a k-dimensional space and you say, well, for 5 data points living in k-dimensional space, and k is, let's say, a high number, right? Let's say k is 1,000, 1,000-dimensional space, 5 data points. You'll see that no matter how you label those 5 data points, you'll always be able to separate them linearly, except for some weird choices of data points. So you can always find a choice of a hyperplane that will do it. That means you are considering too many options. And so VC dimension essentially measures how much you're able to overfit. Because if you can fit to any labeling, no matter how people label things, that means you cannot pick up on any signal. Because that means no matter what happens, you're just going to adapt to it. You're essentially just memorizing the data, right? So that's one way of measuring things. And that theory also shows that I believe it's in n dimensions, if you have only n data points, you can always get everything 100% correct on the training data. So lifting to a higher dimensional space will typically allow you to separate perfectly, but it might be a bad thing, right? Because if you're in a space where no matter how the labels come out, you'll get it right, you're just memorizing those training data points and not learning. Yes? Okay, it's very related. So let's say let's see if I can pull up this slide that I think I hid. So let's look at this slide over here. So some relationship between feature space and kernels. A linear kernel is a kernel where the similarity is just measured by the inner product, and that's this equation over here. So there, now no change to your feature space is the same as using this inner product kernel. So you can implement that kind of similarity or feature space in 2 ways, primal or dual perceptron. You'll get the same result. You'll just have to hold in terms of alphas versus in terms of weight vector directly. Quadratic kernel, k, x, x prime. Quadratic means that you compute this thing over here. Now, this is not an inner product as written over here. This is not written as f of x inner product with f of x prime. It's written as x times x prime, but then plus 1 and then squared. Now, if you work this out, it's actually of this format over here. And what you can read off here is that actually working with this quadratic kernel is the same as working with a feature space that consists of x1 squared, x1, x2, x1, x3. Let's say it's a 3-dimensional original space, x2, x1, x2, 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 x3, x3, x1, x3, x2, x3, x3, and 1. Because if you work with this feature space here, and you inner product in that feature space, you get this expression over here. And that expression over there is the same as this quantity over here. Now, what's the difference computationally? This thing here, you do a lot of products first and then take the sum of a lot of terms. Whereas here, you reorganize your computation such that you can do it more efficiently, right? Here you work x times x prime. If we're three-dimensional, you just have 3 products there, then some sums, plus 1, and square it. Here you have a lot more products and sums in the second line. So this is an example where working with the kernel rather than working in the higher dimensional feature space, you get the computational benefit by working with the kernel. Yes?
So we don't even have to do like manually
Yeah, you wouldn't have to manually add them.
like if we use features, we gotta like add them.
Yes, correct. Yes? Say that again? You want to go down dimensions in some way. What's the motivation? Okay, too many features, sure. We briefly touched upon that last time. But here's the idea. Let's say you have too many features. Let's say we go again with the rule of thumb, factor 5 between amount of data and number of features you can use, right? So let's say 1,000,000 data points. Let's say something small. Say you have 1,000 data points. It means you can just use 200 features with a perceptron as a rule of thumb, right? But let's say your original data space is not 200-dimensional, but even larger, right? So you have too many. What you would do is you would do a feature selection algorithm. And what that means is one example of that is you would select one feature, run the perceptron just using that one feature, and then repeat that for all of the possible features you'd have. Then evaluate on which one did best, pick that one as your first feature, and then you repeat this process. Now, in addition to this first feature, you add a second feature. You have many, many choices for the second feature. You run the perceptron completely for now these 2 features together, see which one is best, and so you keep growing your number of features, taking the most informative additional feature at every round in this process. And that way maybe you'd grow up to 200 features or something if you thought that was the maximum you could do for your current amount of data. You could also go the other way around. You could start from all of them and knock out one at a time, the one that's least harmful to knock out. So you'd have an outer loop that does the feature selection. Yes?
So I see the reason why the Gaussian kernel will be nice, but if it's an infinite feature space.
Yes.
Doesn't that mean that you can always separate the training data?
Yes, so you work with an infinite feature space. You have the problem that if your Gaussian kernel has a very small bandwidth, you'll be able to just memorize everything, and you're just doing essentially nearest neighbors, right? You'll get everything right. And so when you use the Gaussian kernel, to get good generalization, what you'll do is your hyperparameter will be something that sits over here, your sigma squared, and you will run your perceptron with different choices of sigma, see what the score is on the holdout data, and that's your hyperparameter that you tune, and that will say, well, how far does a point really have to reach to get the best performance later? And so if very little data, that sigma probably is going to be relatively large. If you have a lot of data, it's probably going to be smaller because now you have better coverage of the space. And so effectively, you are moving away from the overfitting by choosing the right sigma here. The last thing here, this is an example of what people used to come up with in the early 2000s. You would say something like, how do I measure similarity between strings? Let's say DNA strings, right? 4 possible letters, 2 DNA strands. How do you measure the distance between the 2 of them? Right? And people would come up with all kinds of metrics like, if I were to match an A with a T that's this much similar, a T with a T this much similar, and so forth. If something is shifted over, it's that much similar, and they have some kind of function that computes similarity. Then if you can, for the function that computes your similarity, if you can somehow come up with a feature function f of x, such that f of x times f of x prime is the same as kxx prime, so you find your feature space. If you can do that, then you know that kernel will work correctly with a perceptron algorithm or any of the typical machine learning algorithms. So the key here is when you come up with a kernel that you think is a good one, the way to show that it's guaranteed to work with your machine learning algorithm is to show that there is some feature space. You then don't have to use it, but you just have to show that it exists, and then that's your proof that something like a perceptron will behave the way you expect it to behave, because effectively it's working in a feature space, you're just not touching the feature space. You're working in the dual space. All right, let's take a break here, and after the break, let's look at clustering. So in the second half of the lecture, what I want to look at with you is something called clustering. It's a very different paradigm from what we have looked at so far. So far in machine learning, we've looked at something called supervised learning. There is a correct label for every example that you get to see, and you're hoping to learn how to map from the feature space onto the label. In clustering, there is no such thing. You just get the f of x, so to say. There is no y. Why would you care about that? Well, you get a bunch of f of x's, so a bunch of data, maybe a bunch of images, or a bunch of news articles, a bunch of email, and so forth. And maybe you want to group them. All right. So you could imagine that you somehow understand which ones are similar, put them in a group, and then maybe you send them off to one person who then handles all emails that look reasonably similar. All right. It could be to find categories of customers. Maybe you don't know, based on ahead of time, kind of what a label should be for a customer, and you just look at their purchasing history and so forth and start clustering and say, oh, these look pretty similar. Anomalous program executions. You can imagine that you look at traces or console logs. You cluster based on the text in the console logs. And for now, the clustering is pretty abstract, but just think of it as putting similar things together. And then something comes in that doesn't fall into any of the clusters that you've had so far. You know something funny is happening. That's probably an anomaly. And you want to look at that, inspect it by hand, and see what's going on. You do this when you don't know what you're looking for. That's one of the reasons you do this. It's nice, you don't need the labels. Nobody needs to label, but because you don't have labels, you actually don't control very well what you get out of it. Right? Yes, you get to put in a similarity measure, which will determine what kind of clusters you get, but you don't really know, necessarily what similarity measure to use. In supervised learning, we could have tens, if not a couple hundred of similarity measures, use all of them separately, look at the holdout data, which one ended up being the best, and that tells us, oh, that seems to be the right similarity measure for this data. Here, yes, you can run all 100, but then still you don't know which is the right one unless you start looking at the data and start saying, yeah, I conclude that this similarity measure resulted in a clustering that I like. So it's really for exploration. Think of it as, a baby just starting to listen to what's being said and just kind of picking up on some patterns and realizing some things are similar. So, pictorially, we have stuff coming in. We want to somehow bin it, but they're not necessarily labeled bins. So here's one example. You look in two-dimensional space. You could say, well, here, clustering, what would the clusters be? You could argue for many types of clusters, right? You could say, I think this is reasonable. You could just as well say, well, I think this is reasonable. And then you could just as well say, maybe this is reasonable. So there's a bunch of choices here. And there's no one answer. By just looking at the data, even for this low-dimensional data, we can actually look at it and as a person try to decide the clustering. You can't really decide what the right clustering is without knowing what it's going to be used for. And the best you can hope for is that you have a reasonable way of doing clusterings, feed into somebody, and then they can decide whether that's useful or not, the way you're clustering. So one way to measure distance is this way here, the original nearest neighbor type distance. And so whatever is close, you want to be in the same cluster. So this is used by something called k-means. K-means is probably the simplest clustering algorithm out there, and it's actually used surprisingly often despite its simplicity. So what happens in k-means? This is the algorithm. You pick k random points as cluster centers. The idea is that you're going to represent the cluster by the center of the cluster. And so initially you don't know what the clusters are, so you're just going to pick random points, say those are my centers. Then you do an alternation. You loop around here. First, for each data point, you look at which center is the closest to that data point, and then you assign it to that center. That gives you a grouping, a clustering. After you obtain that clustering, you can now, for every cluster, say, hey, now I know how to compute the center of the cluster because I have a cluster. You compute the center of each cluster, and then you repeat this process, and you can show that if you keep repeating this, this will actually converge to something. Might not be what you wanted, but it'll converge in a finite amount of time. Of all people, I think that's the student who's working with me for research. Okay. Setting the right example. So, if you have this particular clustering here, this set of centers, you could draw a diagram that shows which region of the space is associated with each cluster center, and that's what's shown here. So this is really showing you how the data sometimes would be classified. If a data point fell in a certain region, it would be attached to the cluster center in that region. Now, after you compute the average within a region as your new center, the center will have moved. You get a new decision boundary, and this kind of will iterate over time. So let's look at an example here. The color shows the current clustering. Then we'll compute the mean for that clustering, reassign, and so forth. So this is our initial clustering. Next one, next one. What we see here is that these clusters kind of drift over time. What we see happen is that at the end of the day, you get a clustering that's pretty reasonable. But let's look back at how this actually started. So these clusters are probably the ones you wanted for this particular data set. Initially, it wasn't like that at all. You started with something that looks like this. Say it again? What do the squares mean here? Actually, I'm not 100% sure. Practically, I think what the squares mean is a fast way of computing the nearest neighbors. So the expensive thing in this type of thing is computing nearest neighbors, and it's a way of partitioning your space to effectively compute your nearest neighbors more quickly. Yes? Not sure. So what you see here is that the red cluster straddles, in some sense, two clusters, same for the black one. And if you watch this again, you'll see that somehow the black one starts claiming one of the clusters, the red one then moves over to the other one. So let's watch this again. There we go. So pretty reasonable behavior. Mathematically, what's going on? To prove that this actually converges, we're going to show that this is really doing a hill climbing procedure. And we know if we hill climb and, let's say change one or several variables at a time, keep going up the hill, or in this case, it's going to be down the hill to the bottom, at some point, we'll reach some kind of local optimum, not necessarily a global optimum, but then when we reach that, there's no direction to go anymore, and we have converged. So what is the objective we're hill climbing or hill descending on here? It's the distance between each data point and its current cluster center that's assigned to it. So at any given time, we have a bunch of centers. We can compute the distance for each data point to each cluster center, sum those distances together, and that's a number. And we can show that through this procedure, in every step, this number goes down. What are the things we do? In one step of the procedure, we update the assignments. The cluster centers are fixed, and we assign our points to the nearest cluster center instead of the one that it had before. Now, assigning to the nearest cluster center is only going to be better than the one it had before, or equally good. So that's going to improve our score. Then, once we have all of them assigned again, we're going to recompute the center of the cluster. Now, we're not proving this, but if you have a bunch of points and you look at a choice of point that represents all of them, and you compute from that representative point the sums of the square distances to all the points, the one that will minimize the score is the one that's the average of all your points. So picking the average of all your points as the cluster center is the optimal way to kind of perform with respect to this metric here. So in step 2, we do the optimum for each cluster. In step 1, we do the optimum for each assignment to clusters. So in each step, we improve our score, decrease the distances to the assigned cluster centers, and that means that we are, at some point, we cannot go below 0, so at some point we will hit the bottom of this hill, and that's where we'll stop. Okay, so we looked at this. Updating the means, straightforward. Looked at that. Initialization. How do you start this k-means? Well, one way to start is just randomly picking some points in space. Usually what will work better is that you initialize with some of the actual data points, because that way at least you pick some representative parts of a space. So you randomly pick some data points and start from there. It could completely go wrong. You could have a poor initial choice. You could be clustered in a weird way, and you won't like it. And so typically what you do is you initialize maybe 10, 20, 100 times, and you can then compare after the fact which one has the lowest sum of square distances at the end. That's your best local optimum, and that's just the clustering that you might prefer. So here's an example of what could go wrong. If you initialize this particular way over here, you'll get stuck there. That's your local optimum. From there, you can't do any better. If you reassign the cluster centers, red will stay put, blue will move over there, green will move over there. Then we recompute the assignments. The points will say assigned to whatever they're assigned to now, and you're stuck in a local optimum. If you initialize, however, this way over here, you would find what we could think of as a better local optimum. Yes?
You have to know how many clusters you're trying to separate.
That's a great point. So how many clusters do you want, right? One metric to go with is to say, I just want to minimize the sum of the square distances, right? Because that's my score that I'm really optimizing here. So sum of the square distances to their cluster centers. But then the problem is if you have as many centers as data points, you can achieve 0, and that's not the clustering you want. So one thing you could do is you could do something where you say, oh, let me plot a curve, right? Some curve as a function of the number of clusters. You look at your sum of square distances. Let's call it SOS. And you see like for one cluster, that's probably pretty large. Then 2 clusters would be smaller. 3 even smaller. 4 even smaller. So 1, 2, 3, 4. And maybe here starts saturating and decrease much more slowly. And maybe you pick that kink in the curve, you say, over here, the improvement of an extra cluster is not really worth it, it seems. I'm probably starting to overfit to the data and kind of tease things apart too much, and that's what you would pick. If you really want to get into the theory of picking the number of clusters, we actually have the world expert on picking the number of clusters in Berkeley. I'm not talking about manually picking it by hand. He's not going to sit there and pick the number of clusters for you. But Professor Mike Jordan, around 2003, he essentially, together with his students, came up with what many argue is a really nice way of automatically picking the number of clusters using something called non-parametric Bayesian methods. It requires a lot of mathematical machinery to work through, but it happens to do a really good job. So if you're willing to work through that mathematical machinery, that's even beyond the scope of 281A, you could have a system that picks your number of clusters in a very clean way. Another way to do it is more something like this. You look at the learning curve and then just kind of evaluate where the score has a kink, and you say that's probably the right spot. But if you want to learn more, look up Dirichlet process, Mike Jordan, and that'll tell you the kind of state-of-the-art way of dealing with these kind of choices. Okay, so there's a bunch of schemes to optimize this k-means procedures that are very well motivated by practical considerations. What I want to do in the time that's left is actually move a little ahead. And we know how k-means works. We've seen all of this. What I want to look at now is another type of clustering, which is agglomerative clustering. And the idea there is that you actually, instead of thinking I'm going to partition the data, you think of it as agglomerating close-by data points together and see what kind of clusters emerge. Because if data points are really close by to each other, you kind of have an idea for these should probably be clustered together. And you start in some sense bottom up. You say, I'll start bottom up, see which data points I know really should be together, and see what emerges from that. So it's a very different approach than k-means. So first step is you look at very similar instances, you merge them together, and then incrementally you keep repeating this. So the algorithm would be you maintain a set of clusters. Initially, each data point is its own cluster. And then you repeat. Pick the two closest clusters, merge them into a new cluster, and stop when there's only one cluster left. That's interesting. You end up with one cluster. Why is that fine? What we really get here is you get the spectrum. We talked about how do you pick the number of clusters. This starts with a number of clusters equal to the number of data points. And then it becomes a little less, a little less, a little less. And then after the fact, you could inspect your data along that axis and see where your clustering is most meaningful to you for your use of inspecting the data and trying to make sense of it. So here's an example. You would put those 2 points together. These 2 points here, those are the two closest ones. Then now you have that as a cluster. You look at what are now the two closest clusters. Maybe those two are the two closest, and those two, and so forth. And what you get is this tree structure, dendrogram structure, that tells you how your data is structured. So you get this hierarchical decomposition of your data, which in not many cases can be useful. Keep in mind, clustering is a way of exploring your data. So you might not even have a really right clustering. You might want to look at different scales, more clusters, less clusters, and this allows you to kind of go through the data and see at different granularities what things end up together. All right. When I said closest, there's many ways of measuring closest. Even when we already fixed that we work, let's say, with Euclidean distance, once there are clusters, there are multiple data points in those clusters. And so you could do one thing that is closest pair. So what does that mean? You would look at every pair of points between two clusters and see which pair is the closest. So closest pair would be this pair over here for these two clusters, and that would be measuring the distance between those two clusters. Another option is the furthest pair. What that means is something that you want to make clusters where everything in the cluster is really similar. So there are very different hypotheses about your data. The first thing is saying, if A is similar to B, B is similar to C, C is similar to D, and so forth, then A and D should also be in the same cluster. They can be far apart. As long as they're pairwise all similar, you can find the path from one to the other that goes to very similar points. You're okay with clustering them. The second choice here says that every pair of points has to be really close together to be happy to put it in one cluster. So for different data, something different will work well. Another option is to average. So you just average all the pairs of distances. Go with that. You can do something that's a little closer to k-means, do some kind of min variance optimization. Whatever choice you go with, let's put a star next to this in terms of we're not going to ask you to resolve that. Different choices will generate different clusters, and it's up to you to try many of them, explore your data with different clusterings, and see what's useful for your data. Here's an example of clustering in action. Google will crawl the web, will find the latest news stories, maybe by knowing what are news web pages, what are blogs, and so forth. And then it'll display them to you in this particular way. So one thing that you see here is that clustering is not just about the math of coming up with k-means or agglomerative clustering and so forth. It's also about them finding a way to present your clusters to whoever needs to look at those clusters in a meaningful way. So Google here has a way of somehow putting the maybe most authoritative, in some sense, element of the cluster at the top. It's not computing a mean here. It's not saying, oh, I'm going to compute the mean of this cluster of articles and put that mean up. No, it picks one of them that it thinks is most authoritative, put the first paragraph of that one up there. Then there's another way of measuring which are the next most authoritative ones in that cluster, and then you can click to see even more. So that was their way of visualizing it. It seems to work quite well. Just to keep in mind that there's not always a meaningful mean, right? For text, computing the mean might not be really all that interesting. Now, once you've done the clustering, what you can do is you can then decide for all articles in a certain cluster to run a supervised algorithm that then classifies them into one of these categories, right? So we see clustering at this level over here. This is one cluster. This is another cluster. Here is another cluster, and so forth. And then for each of these clusters, there's some supervised algorithm that then decides whether that cluster belongs to world, business, US, and so forth. So we see two types of machine learning in action here. All right, any questions about the clustering? Okay, good luck studying for midterm 2.